All right, welcome all. This is Mr. Mays, and today I'm going to be talking with you about significance tests. So this is Unit 7, Day 1. And like I said, we're going to call it significance tests. All right? And this makes up the second half of our year where we talk about inferences, right? So this is all based around the idea of taking samples and in new, mind-bending, cerebrally defying ways, we're going to expand the notion of what those samples can mean to reach or capture a greater parameter. Okay. Now, you might remember last unit when we were doing confidence intervals, the way that tended to work was we would take a single sample. In this case, I'm going to use the example of p-hat, right? So a proportion. And we would use that to go from a single value all the way out to an interval, right? A set of values. And that was really, really useful because what that did was it allowed us to take, instead of, for example, let's say our p-hat in a particular instance was 0.75, it allowed us to go from that singular value of 0.75 to a set of values, right? Where 0.75 would be the middle value. And we would have a plus or minus. And we called that a margin of error. And in this case, let's say it's 0.15, so that would mean from 0.6 right, to 0.9 in this case. And the beauty of what that did was it gave us a range of plausible values. And we would do a little bit of evaluation work, if you remember. We would do things like if someone said, hey, I think, let's say that this 0.75 is the proportion of students who don't sleep enough at Alexandria City High School, okay? Well, what this would mean would be that the plausible values of proportions of students who don't sleep enough is between 0.6 to 0.9, which is ridiculous, frankly, right? That would mean almost 90% of students would be a plausible value. But then if someone were to say to you, I think, 30% is the answer, you would be able to say, well, that's quite unlikely to be true. That's not a plausible value. And you would say that based on this idea that it did not sit in your confidence interval. Okay, now that's wonderful, but one of the issues that it hits on is because we know that when we run confidence intervals, we're not sure which ones are the ones that actually capture the true parameter. We live in this world where, we have a confidence level, 95%, for example, but we're never quite sure when we're capturing it or when we're not capturing it. And it's also kind of a bit of a problem if we want a little bit more information about a particular statistic. So let me give you an example of what a significance test, a significance test situation might look like here. So if I were going to do a significance test, first of all, I would normally give you, a beginning, a null proportion, right? We write that as a p with this weird zero at the bottom, right? This is just the null proportion. So the null proportion is normally what we call the status quo, right? It's whatever we want to hold as true. And so the example I'll give is, it is believed that 75% of ACHS students don't sleep enough. Okay. So this would be the beginning, in a lot of cases, of what we would call a significance hypothesis testing scenario, right? It is believed that 75% of ACHS students don't sleep enough. Now, before I go through the rest of this problem, we've already been given a key piece of information. We've been given what's called the null hypothesis. Okay. The way we write that is we write an H with a zero in the subscript. That's our null hypothesis. And what the null hypothesis is is that the true parameter P is equal to 0.75. That's it. That's our null hypothesis. And as we'll learn later on, we'll also have to define that parameter, right? The parameter of interest is the true proportion of ACHS students who don't sleep enough. Now, I hope you're rolling with me. We're going at like a really neat, chill pace today. And I want us to do that for this 7.1 unit, because as we move further into it, it's going to be a lot more complicated. And obviously, day 2 and day 3 notes are going to require a lot more math from us. But I want to make sure that we're rolling at a pace where we understand where we're going with this, right? Because similar to confidence intervals, the overarching ideas allow us to delve in to a much deeper degree. But we must understand what is theoretically going on here. Okay, so we have our parameter of interest, okay? And we've even stated a null hypothesis. On top of setting up that null hypothesis, we have also ignited said null hypothesis. Written it out, you might say. Okay. Now we got to move on to the second half of our problem. If it's believed that 75% of ACHS students don't sleep enough, and that's the whole thing, regrettably, we don't really have anything we can solve for here. So if you saw us on an AP exam, you might just be like, hey, thanks, guys. Really appreciate you guys giving us literally nothing to do. I'm going to rock and roll, maybe go for a walk, hang out with some friends, drink a Gatorade. But lo and behold, there will be a second half to this problem. You think the true proportion is. Now, I want to say something really quickly. Before I finish this one out and choose an answer, there are actually 3 different pathways that we could follow, resulting in 2 different outcomes, for the most part. As you'll see next lesson and the lesson after, there will be 3 different calculations, but there are 2 overarching types of calculations. You either think the true proportion is greater, you think it's less, or you think it's not. Those are your 3 options, right? And this sentence here is actually the setup for what we call our alternate hypothesis. And all that the alternate hypothesis is, always in any study, is it's the thing that we are trying to show is more likely than the null. It's what we're using and what we're in favor of over the null hypothesis. And remember, we're a rebellious group. You know I'm a rebellious teacher, and you guys wouldn't be such great students if you didn't fight the power on the regular, right? So when we take a look at something like this, we're always going to favor the alternate hypothesis, and we're trying to do our due diligence to show that maybe there's a stronger argument elsewhere, right? So the null hypothesis here is one of 3 things. I'm going to write all 3 of them out as possibilities. Now, in any given problem, you will only have 1 alternate hypothesis. But the 3 options, as we said, are greater. The parameter is actually greater than 0.75. 2, the parameter is less than 0.75. Or 3, the parameter is not equal to 0.75. And the thing I want to kind of highlight for you here is that these first 2 options are called one-tailed tests. And this second option here, I'm going to put in red, or I should say third option, is called a two-tailed test. Okay. Now, in order to explain why this is the case, I'm going to do a little bit of a graph for you. Now, you're going to remember, because you are incredible and brilliant, and you've been in my classroom, so you've been rolling with the master, as it were. You're going to remember that the way that we make inferences in general is with a sampling distribution. A theoretical framework of a bunch of samples, all of the same size, that we use to understand a particular topic. Okay? So what I want you to imagine for this is a sampling distribution where the mean of that sampling distribution is the null hypothesis. Okay? So I'm going to draw a relatively normally distributed one. And just as with the previous unit, we must have it be normally distributed. And this will all come in for 7.2 and 7.3 notes a lot more. But just be aware, we're still going to need the same situations. Independence, a relatively normal distribution of sample data. Or I think more importantly, I should say, not the sample data, but the sampling distribution itself must be normally distributed. Okay, so that means for this data, we would expect, for example, in our particular scenario here, 0.75 is going to be sort of the mean of this data. And of course, let me draw a bunch of bars. Imagine that each one of these bars contains a bunch of different samples, all of the same size, that vary ever so slightly from a proportion of 0.75, right? From that mean, right? Because as we know, this null proportion here, right? This null hypothesis value, there's a certain amount of error that could be seen from one way or to the other of that particular value, right? And there are odds that reach far out to the left and odds that reach far out to the right that become less and less and less likely as we travel away from the mean, right? And as you could probably imagine, if I took a sample of 100 of you guys, right? And I found that the proportion was like 76% of you don't sleep enough. You'd probably say to me, Mr. Mays, it's pretty clear to me that 75 is a pretty strong estimate for the truth, right? And if our sample is slightly off from that, we would call that a bit of standard error, right? Or sampling error, and that would make a good amount of sense, right? We're not going to always hit the exact proportion that we expect from the null hypothesis, right? Even if the null hypothesis is true. But the whole idea here for significance tests is, well, how far away from that mean does my sample have to get before I have a strong enough argument to be like, this isn't going to make a lot of sense, right? What if my sample's out here? Is that far enough away from my center? What if it's way out here? I would argue if it's way out here, right? And as we're soon going to see, it's not just going to be me arguing it, right? It's going to be some math that we do to show it. I would say, though, if we were way out here on the fringes of these odds in our sample, and our sample was following all the rules we love a sample to follow, right? Replicable, large enough sample size, random, all these beautiful things. Independent, normally distributed. If all these things are the case, then we do not have to worry about this potentiality that we don't have a leg to stand on when we're arguing against the null hypothesis. When we're saying, hey, maybe this is wrong, it could be true if our sample data is way far away from that central point, right? Either to the right or to the left. Or potentially to the left and to the right. And that's what these mean. When I say a two-tailed test, I mean, hey, is my data either way too far away from the right or way too far away from the left? Either one of those will be okay for me. And that's p is not equal to 0.75. And then the two one-tailed tests are either p is greater than, which is this upper tail over here, or p is less than, which is this lower tail over here. I'm going to cough very momentarily while you drink this beautiful knowledge in. All right, and we're right back at it. So hopefully what you're noticing here is we've got a lot of interesting ways that we could go about saying, hey, maybe this is a situation where your null hypothesis that you're telling me is so true, that it may be false. Well, what do I need for that to be proven? Well, I'm going to need some sample data. And of course, that will be the next part of the question, is once we pick one, let's say for this particular example that I'm giving you, let's say that we think the true proportion is actually less. What if we think you guys are a little bit less sleep deprived than 75% of you, okay? So for our particular option, we're going to say, you think the true proportion is less. okay? And then I give you some sample data. And let's say I'm going to make it really, really, really obvious for us here. Let's say you get 32 out of 100 students saying they don't sleep enough. Oh. See, again, got those lovely chill vibes rolling through here. All right. So already, I just want to reiterate these concepts. Hopefully you're going to reiterate them with me. You should be saying, all right, if I were to set my parameter, I already know what my parameter is. We set it up here, right? The parameter of interest is the true proportion of ACHS students who don't sleep enough. What's my null hypothesis? Well, my null hypothesis is, of course, that the parameter is equal to 0.75, because that is what I have been told by authority figures. On the other hand, my alternative hypothesis is that that parameter is actually less than 0.75. You'll notice I don't put my sample data in for my alternate hypothesis. I always, always, always put in the proportion that's used for the null hypothesis, but I just make a comparison point here. So we're going to be doing a one-tailed test here, okay? And what I'm trying to do is use this sample data with a p-hat of 32 over 100. Which of course equals 0.32. Okay, so we have our p-hat, right? And we also have our null proportion. Again, the null proportion is the one that is presumed to be true by authority figures, but that we are going to go and fight. And effectively what we're doing is we're going to imagine a sampling distribution, all of sample size in this case, 100. And that will vary depending, obviously, on the problem. They will tell you what the sample size is. But in the one that I've given you here, the sample size was 100. So what's kind of cool about the theoreticals of what we're doing here is we're imagining a sampling distribution that's focused around the null proportion, but we're imagining it in sample sizes for the way that we got our p-hat, right? Where n is equal to 100 in this particular instance. And that will vary depending on the question and what's provided. And in that, what we want to find is what we call, and you're going to have to forgive me because we're using the letter P yet again. It's because we love the letter P in statistics. Let's use this sort of hunter green, if we will. We're looking for what's called a p-value. And the p-value is very important. I want to scroll up here for a second. This green over here, these low and high ends, those represent relatively small p-values. And what a p-value is a p-value is the odds of observing your p-hat or sample data. Actually, let me, to be more humanitarian and open-minded to also our means that we'll be doing soon, the odds of observing your sample data or more extreme. And when I say more extreme, hopefully you're filling in the gaps with me. When I say more extreme, what I mean is if I wanted to find less, right, like in this particular instance, then it would be, and even lower. Or if I were looking at values greater, it would be my value or even higher. But in ours, in this particular instance, right, we are interested in less, right? So it's the odds of finding sample data of 0.32 or lower. Given that the null hypothesis is true. Now, is the null hypothesis true? No. You may remember in class I brought up something called a reductio ad absurdum argument. And what a reductio ad absurdum argument is, and you don't need to know this for the AP exam, but you may want to know it just for interdisciplinary work of all wondrous kinds, is an argument where you take a thing that people treat as true and you apply it in a bunch of situations that show how silly that argument can be. It's basically like, instead of saying your argument's dumb, I'm going to tell you every reason, you kind of use a person's argument continuously to show them all the flaws it has. Excuse me. And that is effectively what we are doing here with our established p-value. We're saying, oh, you think your null proportion is so wonderfully true? Well, if it is, let me tell you how unlikely it is to get my sample data, or more extreme, if it is true. So, a few things that you may be able to take away already. As your p-value gets lower and lower and lower and lower and lower, right? More and more extreme, small and small and smaller, either on the high end or on the low end, like we said, it can be on either end, either tail of the distribution of conceivable values where the null proportion or null hypothesis or null mean, as will be the case later on, is the center. As the p-value goes down, right, we become more likely to reject the null hypothesis, right? And as the p-value goes up, we become less likely to reject the null hypothesis. And at the end of any significance test, we are doing one or the other. We are either rejecting the null hypothesis, which we feel good about, that's why that's in yellow, or we are, and let me write it out, failing to reject the null hypothesis. Those are our two options. We either reject the null hypothesis or we fail to reject. We never accept the null. We never do that. Do not accept the null hypothesis. Why? We're stubborn. Also, why would you accept the argument of an authority figure just because you were unable to disprove it? The wonders of science and math and all of the careers of facts and knowledge are that not that we're forced to agree to things in subservience, no, rather that we continue to question them and admit when we cannot reject them, but we are not forced in any way to feel a sense of fealty to them. Okay. We've got a lot of things going so far. So far, we should have a pretty solid understanding of this idea of how we use a sampling distribution to create a range of values around a parameter value that is formed by what's called the null hypothesis. And that's just whatever the status quo is, whatever the readily established thing is. In the case of this example problem I've given you, it's believed that 75% of ACHS students don't sleep enough. We should be rolling along with this chill pace. Again, I told you I was feeling a chill day today, and I think it's really going to feed us. Yeah. And alongside that, we should be understanding this concept of the alternate hypothesis. We should understand that there are either two-tailed or one-tailed options, and there are two ways that a one-tailed option could look. A one-tailed test, I should say, versus a two-tailed test. It really has one way that it looks, right? Once we have that understanding, we also understand the way in which we use sample data in order to make our argument. Now, luckily, you're not going to have to calculate one of these until next class. But in the meantime, there's something you should understand, which is that obviously there should be a sort of cutoff point. Right? You say, as the p-value gets lower and lower and lower and lower, we're more likely to reject the null. Well, when do we reject the null, right? And that cutoff point is known as the alpha. Right? We write it with this wonderful fish symbol. In class, I worked to perfect it, and there it is. The alpha is very often 0.05, right? Also known as 5%. Remember, never accept the null. Why is it 5%? Well, as you can imagine, unlike last unit, right, where we were very focused on like the middle 95% of data or the middle 99% of data, this unit we're very focused on the fringe data, right? Because we're saying, what are the odds of getting a really unlikely value? And are they so unlikely, again, my p-value, that I can say, hey, you're wrong, I reject you, right? So that means in significance tests, unlike confidence intervals where we're looking for the 95% confidence, we're actually looking for the 5% unlikelihood, right? So the alpha is like the cutoff. It's the gate. It's like if you can get a value lower than the alpha. So if your p-value is less than the alpha. Ooh, let me get that, excuse me. Let me get that alpha looking pretty again. I want it to be a nice, there we go. Then you reject the null hypothesis. But if, on the other hand, though, if your p-value is greater than the alpha or equal to the alpha, even if it's equal, then you fail to reject. The null hypothesis. All right, and that should make a lot of sense, right? So again, what this is saying is, if I can prove, right? Another way to think of it. If, I should be using, let's do it like a blue. If I can show beyond a reasonable doubt and how do we define beyond a reasonable doubt? Well, in U.S. judicial systems, as we talked about in class, that's a very vague concept. But in statistics, there is truth to that, right? Less often than the percentage, or I should say the probability is the truer reality. Set by the alpha. Ooh. We do my fish symbol instead. Oh, that's an ugly fish. Mr. Mays masters fishes. Okay, if I can show beyond a reasonable doubt, aka if I can show that less often than the probability set by the alpha, right? That is how often you will get your sample data. Then I get to reject the status quo. So if I can show beyond a reasonable doubt, right, essentially that my sample data is very unlikely if the null is true. And that's what we're doing. We're saying, hey, take your null hypothesis. If it's so true, here's how unlikely it would be for me to be able to get the sample data I got. And I got my sample data effectively. And this is the wonder of statistics. You, a singular individual, are fighting the claims of an entire institution. And as long as you have a strong enough sample size, which is not even that wild of a sample that you have to create, right? Even 100 people is a strong sample size oftentimes, right? If you can do that and show that this would normalize in a curve and it rejects or fights the trueness of this particular null hypothesis, then you get to say, hey, I reject you. I've shown sensible evidence against your claim, right? Okay, so what you'll notice then, therefore, is that it's important for the sample data to actually go against the current of the null proportion data or the null mean data, and that will help us. Okay, hopefully you understand what I mean when I state an alpha. That's just our gate, right? And the most common alpha is an alpha of 0.05 or 5%. That's 95% confident, right? And what that also means, if you think about it, is 5% of the time, you're going to see, and this goes back to my curve up here, that means about 5% of the time, you're going to see data like my data, right? If the null were true. Excuse me. Only 5% of the time, you will see data like my data, if the null were true. And that's so unlikely, or I should say less than 5% of the time. And that's so unlikely that we're willing to say, hey, I reject the null. Okay, that's too unlikely for it to be a strong argument. I can reject that argument. Other ones that are commonly used, 90% confident is another, 0.1, right? And then like the sort of most discerning, also most difficult to get, would be 99% confident. All right. So we've gotten through a lot of really big concepts here, and hopefully you've also gone through the slides, I should say, that accompany the 7.1 days video notes, etc. There are two final things I want to leave you with before I kind of let you go into the wonders of the world, and they are as follows. 1, I want you to turn to slide 23, if you would, in the 7.1 slideshow. If you don't have that in front of you, that's okay. I'm actually going to kind of draw it out for you right here. I want you to keep in mind there are two possibilities with any situation. Either your null hypothesis is the true hypothesis or your alternate hypothesis is true. And we don't know which of these is the case, but I want you to keep in mind, right, the reality of life is that either the null is true or it's not true, right? And if the null is either true or not true, then the alternate is also either true or not true. Now, there are also two outcomes. You either do not reject the null, right? Or you do reject the null. Oh, not reject. This is not a carburetor. Reject the null. Thank you to anyone who gave a laugh out there for my mechanic speak. In favor of the alternate, right? Okay. So you either reject the null or you don't reject the null. And the null is either true or the alternate is true, right? So if the null is true and you do not reject the null, then you're good to go. I'm going to put a little check there. Bada bing. That's a beautiful thing, right? We are good to go. We have succeeded in noticing that the null should not be rejected because it is true. Similarly, if the alternate is true and we reject the null in favor of the alternate, we are good to go as well. And I want to state that that is called power, right? Or what I should say is power, the percent of times my test, right, with my sample data rejects the null given that the null is false. So that's very important. We call it power because power is the percentage of the time that you effectively reject the null with the assumption, right, the understanding that the null must be false. Excuse me. Now, is the null definitely false? Well, we don't know. We're not sure, but we call it the power of our test. Now, calculating the power of a test is sadly a bit of a complicated measure, but I just want you to understand when someone says, oh, I have a powerful test, that's not always just like a good thing, right? That just means that the test is really, really effective at catching, or I should say rejecting the null, but with the assumption that the null is not true, right? That the alternate is actually true. So power is good, but we don't want too much power because otherwise we run the risk of what we call a type 1 error. And what is a type 1 error? Well, a type 1 error is when you reject the null when the null is true. So type 1 error, when you reject the null when you shouldn't, right? On the other end, what about the opposite? Well, that would be a type 2 error. A type 2 error, is when you fail to reject the null when the null is false. Right? Type 1 error is when you reject the null when the null is true. Type 2 error is when you fail to reject the null. Okay, and you will already notice just in this little pattern, this little 4 square that I've built out for us, a couple of trends. Right? As power goes up, and this should make sense, do not just memorize what I'm about to say. Talk it through with yourself to make sure it all connects. As power goes up, right? This is also on the last slide of the notes. Type 2 error goes down. And that should make sense if we take a look here. Type 2 error is the risk that you do not reject the null when, truthfully, the null is false, right? The ha is true, or the alternate, I should say, is true. And if your power level is super, super, super high, you're really, really, really looking to reject the null. You're, in fact, quite likely to reject the null. Overzealously, one might say. What you're not risking is accidentally not rejecting the null when you should. So as power goes up, type 2 error goes down. But type 1 error goes up. And that should make sense, right? And type 1 error, if you think about it, type 1 error is measured by the alpha. This is my sort of full circle moment with you. So remember we were setting what the alpha is, right? What the alpha means, for example, in a 5% alpha situation or a 0.05 alpha situation is 5% of the time, or just under 5% of the time, we accidentally commit a type 1 error, right? So alpha of 0.5 means 5% of the time we commit a type 1 error. And what is a type 1 error? Well, as you know, a type 1 error is when we reject the null when we should not have rejected the null. The null ended up being true. Okay. So another way for power to go up, as you may notice, right, is going to be a situation where the alpha is greater, right? If a type 1 error goes up, that also means you could have a greater alpha. Right? If my alpha is like 30%, like a 0.3 alpha, that's going to increase the type 1 error likelihood. It's also going to increase the power of my test, but to a detriment, right? And the last thing that happens as power goes up, or something that increases power, sample size goes up. And that's a good thing, right? Bigger samples make for more powerful tests. Why? Because we're more certain in our results. Okay? Now, you should be very, very proud of yourself if you followed along with me here and there. What have we done? We've understood the concept of power, and we've understood the concepts of type 1 and type 2 errors in the opposing order. We've also looked at how they relate in terms of the truths of the null hypothesis and the alternate hypothesis in various scenarios. We've understood the alpha as sort of a gateway for us to understand how likely it is for a particular outcome to occur. That's been useful for us because it allows us to grasp a p-value, which we will compare to the alpha, right? And if the p-value is less than that alpha, we can reject the null hypothesis. Whereas on the other hand, if the p-value is greater than or equal to that alpha, we fail to reject the null hypothesis. We have understood the value and the power now of taking a single sample and using it to compare against essentially a null hypothesis that everyone takes to be certain. And in doing so, we can do a more directed study, a more directed argument against a particular statistic than just looking at a confidence interval and seeing what does or does not lie in that interval of values. And that, heroes, legends, is the power of a significance test. Tune in next time with 7.2 to see how we can do this with a proportion in real time, using both your calculator and your algebraic minds to apply math to that next and most beautiful plane, where truth becomes apparent to us and ever-growing, ever-changing. I adore being your teacher. Thank you for going on these brilliant journeys with me. This is Mr. Mays, signing